Let's look now at section 2.6, and let's talk about transformations of graphs. We've seen the linear equation and its graph, and we know that every time you have a linear equation, you have a straight line. And that straight line might be slanted up or slanted down. It may be horizontal or it may be vertical. But in every instance, it's a straight line. Because it's a straight line, we have a relatively easy time graphing it. Since we already know what the pattern should be, 2 points are enough to give us a line. However, if you don't have a linear equation, it could take you a substantial amount of effort to find enough points to graph. That is, if you don't know what the shape of the graph is ahead of time. For example, if we have these 4 points, and we say, okay, we're going to go ahead and graph something through those 4 points. We don't really know what that graph is. It could be this sort of a U shape, or it could be more of a V shape. It could be something like this. It could even be a circle. And if you think about it for a few moments, you probably come up with another 100 different ways that you could plot a curve through these 4 points. So if you don't know what your graph is supposed to look like ahead of time, then you have to find a lot of information before you can graph. However, if you know the basic structure of your graph, the basic shape, then a lot less information is required. One way to think about a graph is as a collection of points. You can think of a graph as here are 50, 60, 70 points that I'm connecting with some line. But another way we might think about a graph, in fact, a very useful way we can think about a graph, is as a whole. Meaning it's not the collection of 100 points, rather it's a single object. Right? For example, here's just something I grabbed off my desk. Now, this is made up of billions of atoms. Right? It's made up of thousands of little pieces of plastic, or it's made up of, whatever you might want to call it. Whatever you might want to say it's composed of. But we don't really think of it this way. If I have this object right here, I could say, just go ahead and move it up 2 inches. There we go. We've moved it up 2 inches. I didn't really think of, okay, I'm going to have to take this little piece of plastic and move it up 2 inches, and take this little piece of plastic and this one, and let's make sure all the ink also goes up 2 inches and so forth. We just thought of it as a single object. Right? If I take this object and I say, okay, now go ahead and flip it upside down. Well, there we go. I didn't have to think about, okay, here's this little white piece of plastic needs to come over here, and this ink needs to come up down this way, and then this part of the tape needs to rotate, and then this part's going to stay right where it is. None of that. I just said, here, flip it upside down, or flip it this way. If you can think of an object as a single object, then it's very easy to describe what happened to that object. It moved up, it moved down, we moved it to the left or to the right, or we flip it upside down, or we flip it left to right. Something like that. We want to do the same thing with a graph. If we think of a graph as a collection of hundreds of points, well, there is some utility to that. There is some utility to realizing that we have hundreds of points that are solutions to an equation. But what will be also very, very useful and make things a lot shorter in some cases is to think of a graph as a single object. As such, let's go ahead and talk about some very basic functions. We've already seen the linear equation. Let's talk about a few others. Let's talk about the quadratic function. Okay? What I'm going to do here is I'm going to define a few very basic functions. You say, what do you mean by basic? You mean easy? No, basic doesn't mean easy. Basic means it's a basis, meaning we're going to base everything on this. That's what the word basic means. Everything else is based on that object. We're going to have a few basic functions. Here, we're going to call these parent functions. And our parent functions are going to behave kind of like parents. They're going to be where we're going to start from, and then they're going to have children functions. We're not going to really carry that language very much further, but here I do want to call these parent functions to indicate that other functions will come from these. Okay, so this is not an arbitrary quadratic function. In fact, it's the simplest quadratic function that we can come up with. All right, so what is the simplest quadratic function? It's the one that is just barely a quadratic function. It's f of x equals x squared. Whenever we see a parent function, what we want is we want the most basic function. We want the one without any extra stuff. We want the simplest function that still fits the category. As such, we won't have any pluses or minuses. This won't be plus anything or minus anything. It'll be the simplest function of that category. Here, this is a quadratic function because if you imagine this replaced with a y, that's y equals x squared. That's the quadratic equation. Right? That's a quadratic equation. Whenever you have a quadratic function, the graph of a quadratic function will always look something like this. So this is the graph of f of x equals x squared. This shape, much like we had lines before, this is called a parabola. And this is the graph specifically of f of x equals x squared. However, in this coming section, we're going to see how we can take this basic function and modify it. Other quadratic functions, even though they're going to be different from this one, are going to have a graph that looks like this, albeit it's going to be modified. We're going to take this thing and we're going to move it up or down or left or right, or we're going to flip it upside down or flip it left and right, and so forth and so on. So here, these are not the results, rather these are where we're going to start from. Once we know what the basic shape, what the basic structure of an equation is that fits this category, then we can modify that structure to give us a more complicated graph. So here we're going to list a few parent functions. This is not an exhaustive list. There's going to be plenty more where this comes from. However, here we're going to start with just a few so that we can get a little practice in on how we can use this concept. So here we're going to talk about the quadratic function. The next one we want to look at is the cubic function. And the cubic function is the most simple, the cubic parent function is the most simple cubic function. We're not saying plus anything or minus anything or times anything. It's just x to the cube, hence the name, the cubic function. Here you say, well, how come that's called a cubic because of a cube, and this one's not called what does quadratic mean? This comes from Latin. Anyone who speaks Spanish, cuadro, literally a square. So sometimes sometimes it's named in a descriptive way, but sometimes the language that it was named in is not the language you speak, right? So in this case, in Latin, quadratic. Anyone who speaks French or Spanish, cuadro, that's a square, literally a square. So here, a cubic function. Anytime you have a cubic function, it's going to look like this. And it'll be this object, and it'll be modified in some way, but basically, it'll look like that. Okay? Aside from the quadratic and the cubic, we're going to have the root functions. Here we're going to take the square root function. And that's f of x equals the square root of x. All right, for obvious reasons, the square root function, because it's the square root of x. And anytime you have the square root function, the graph is going to look like this. And depending on what other things we have here, this will be modified in some way. But basically, every equation that fits the category of square root function is going to look like this. We're going to have the cube root function. And that's f of x equals the cube root of x. And every cube root function, everything that falls into this category, will have a graph that looks like this. And it'll be modified in some way depending on exactly what the equation is, but it'll have this structure. We're going to take the absolute value function. And again, it's named for the operation. It's the f of x equals the absolute value of x. And if we take a look at a graph of that, that's this V shape. These are both straight lines, and they continue on in both directions going up. And finally, the last one we're going to look at right now is what's called the reciprocal function, because f of x is the reciprocal of x, or in other words, 1 over x. One thing to note about all of our parent functions is that they all pass through the origin 0, 0, 0, 0, 0, 0, 0, 0, and 0, 0. This is the only one that doesn't. However, even in this case, 0, 0 is going to play a role. These red lines that I'm drawing here are not part of the graph. However, they do help us when making the graph. We'll talk more about these in detail later, but these are called asymptotes. And asymptotes work as the skeleton, and they work as a support structure for your graph. Essentially, they tell you your graph is going to follow along these rigid lines. So here, your graph is going to follow those dotted lines, and depending on what graph we have, the asymptotes will be different. But for the most basic one, for the parent function, the two asymptotes cross at the origin. So again, these red lines are not part of the graph, but they do help guide where the graph goes. So here's the reciprocal function. Okay, so these are going to be our parent functions. There's nothing particularly special about these other than they only have a single operation. Notice this is x squared. No plus anything or minus or times or anything like that. There's a single operation, and that's a square. Same thing here. There's a single operation, and that's a cube, a single square root, a single cube root. Here we have one operation, and that's the absolute values. And here we have one operation, and that's the reciprocating here. All right? That's what makes these parent functions. They have exactly one operation. There's nothing special about these particular ones, and in fact, in Chapter 4, we'll see a few other equations, a few other graphs, which can also be categorized as parent functions, and we'll see that in Chapter 4, namely the exponential and the logarithmic functions. But for now, these are good enough, and they're good enough for us to practice what we're looking at in this section. So these we're going to treat as objects. Yes, there are points along these curves. In fact, there's a lot of points. Right? There's lots of points everywhere along each one of these curves. But we're not going to treat these graphs as a collection of points. They are a collection of points, but we're not going to treat them that way. Instead, we're going to treat them as a single object. Now, this single object, we're going to be able to move it. We're going to move it up or down, left or right. We're going to flip it upside down, or we're going to flip it left to right. Right? These are called transformations. They are going to allow us to transform our parent functions, the simplest versions of each of these functions, into more complicated versions of themselves. Meaning, okay, that right there is the cube root of x. What if I want the cube root of 2x plus 7? How do I do that? How do I get that? So let's take a look at what different transformations we have and what they do. All of these are transformations. I'm going to go ahead and list them all first, and then we'll see some examples. These are all transformations. However, we're going to categorize them based off of what they do. The first kind of transformation is going to be a translation. And a translation is the kind of transformation that moves things up or down or left or right. It doesn't change anything about the object. It doesn't change its direction or its orientation or anything like that. It only changes where it is. Right? Translations are caused by addition or subtraction to the parent function. So here, let's go ahead and start off with a parent function. And here, I'm not going to pick any specific one. Let's just say let f of x be a parent function. And it doesn't matter which one it is. We have 6 different ones to choose from for now, and several more later in the next few chapters. All right? So let's just say you have a parent function. Doesn't really matter which one. All right, so what does a translation do and how does it do it? Well, again, translation moves things. And the way they do it is through addition and subtraction. So let's say you have your parent function. Well, you can add something to it. You can take your f of x and you can add some number. Now here we're not going to be specific about what number, it's just you're adding a number. Whenever you add a number to a function, what you're doing is you're moving everything up by c units. On a graph, it would move up that many steps. Well, if adding moves things up, then it doesn't take much imagination to think, well, what is subtraction going to do? It's going to move things down. So this will move things down c units. Now, when you add or subtract, there's more than one place you can add or subtract. You can either add to the function as a whole, subtract to the function as a whole, or you can add to just the variable. You can subtract from just the variable. So here, I have f of x plus c. I could have f of x plus c. Notice, instead of adding c to the entire function, I'm only adding it to the variable. And same thing over here. I can, instead of subtracting from the whole function, I can subtract from just the variable. This is also a translation, but it is going to move you not vertically, but horizontally. Here, this will move things to the left c units, and this will move things to the right c units. That might seem like I said that backwards, right? You would think pluses to the right, maybe. Usually pluses to the right. But in the case of transformations, when you add something to the argument, when you add something to the variable of your function, you're moving everything to the left. That is not a mistake. That is correct. Same thing here. Subtraction is going to move everything to the right. Okay. We're going to see some examples of this here in just a moment. For right now, I'm just going to list what the transformations are, and then we'll worry about looking at how they work with different examples. So translations move things either up or down or left and right. The next kind of transformation we're going to have is called the reflection. Okay? So translations take an object and either move it up or down or left or right. Reflections aren't going to move the location of the object, they're going to change its orientation. They're either going to flip it upside down like this or flip it left to right this way. There's 2 ways you can reflect things. 2 ways you can flip it. Reflections are caused by multiplying by a negative number. So here we can say, all right, I'm going to take f of x and I'm going to multiply by -1. Well, again, just like up here, I could either multiply to the whole thing or just to the argument. So that is going to cause 2 different kinds of reflections. If you take the entire function and multiply by -1, that's going to flip everything upside down. The way the textbook says it, it flips things vertically. Upside down, I think, is a little more common for people to remember. However, formally, the way this should be said is it's going to reflect vertically. That's the formal way to say it. This is the way most people remember it. It's upside down. F of minus x, if instead of multiplying by -1 on the whole function, you multiply just the argument by -1, this will flip things left to right. And again, the formal phrase would be you're going to reflect horizontally. So flip, you have your object. If you multiply by -1, it flips everything upside down, top to bottom. If you multiply with just the argument, that's going to flip things left to right across the side this way. All right, now, here I multiplied by a -1. When I say, well, why did it have to be -1? Well, that's what causes a reflection. Well, yeah, but couldn't I multiply by -5 What about negative 12? What about a positive? Wouldn't multiplying by a positive number do something? So that's going to be our third type of transformation, and this is called a dilation. Dilations are a transformation that causes a change not to the location or the orientation of an object, but rather its size. Here I've been using this object as an example, but that's not a very good, this won't work very well for this kind of example. So I'm going to choose a different object. And yeah, I have one of those. There we go. A rubber band. A dilation is going to cause you to change things. It's not going to change the nature of the object. Here, this is like a, an oval. It's not going to change it to a different shape. It's not going to suddenly change it to a triangle or a star. It's still going to stay an oval. But, in fact, it's not even going to change its location. It's not going to move it up or down or anything like that. Rather, it's simply going to change its size. And the way it's going to change the size depends on exactly what we do. Notice there's different kinds of translations and different kinds of reflections. Likewise, there's different types of dilations. Your dilations will stretch things either horizontally, making them wider. Notice when you make it wider, you're not making it any taller. It's still the same height. It's just wider. The other kind of dilation will make things taller. It won't make them any wider or narrower exactly. It's just going to make them taller, like this. So a dilation is like stretching your object. It's not going to change its shape. All right, it's still an oval, and it's not going to change its location. I didn't suddenly move this up here or anything like that. Rather, it's going to stay in the same shape, basically, and in the same location, but rather it's going to simply make it wider or taller. Like that. So that's going to be caused by multiplication by a number other than 1. Right? So we're going to keep these separate, really. If you multiply something by a number, that's a dilation. If you change its sign, that's going to be a reflection. And you say, well, what happens if I do both? What if I multiply by like negative 5? That's a number other than 1, but also there's a negative. We'll see how to treat that in a moment, but basically what we're going to do is we're going to have two different transformations at the same time. So here we're going to say, okay, a dilation, you're going to multiply your function by a number, and again, we're either going to do it on the outside or on the inside. If you multiply on the outside, well, it depends on what number you're multiplying by. This is going to make things either taller or shorter. Right? When you dilate something, you can make it taller. You can also make it shorter. You can squeeze it down. So depending on what C is, you're going to make things either taller or shorter. So here, if C is greater than 1, if you're multiplying by 2 or 3, or even 1.5, if you're multiplying by a number greater than 1, then you're going to make everything taller. It's not going to make anything wider, just taller. Okay? On the other hand, if C is less than 1, now again, we want everything to be positive. Negatives are going to fall into the category of reflections. So here, C is less than 1, but we're still going to keep it positive. That's going to make everything shorter. On the other hand, if we have your function being multiplied by a constant in just the argument, here we're multiplying on the inside rather than on the outside, we're going to make everything either wider or more narrow. Okay? So just like before, it's going to depend on what the value of C is. If C is greater than 1, the whole thing's going to get more narrow. Or in other words, it's going to get squeezed in a bit. Like this. It's going to get narrower. But if C is less than 1, and again, we want it to be positive, negatives will fall under this category, then that's going to make everything wider. And there we go. These are going to be the three types of transformations that we study in this section: translations, reflections, and dilations. There is a fourth category of transformation, but we don't do that in this class. The last category is a rotation. You can take this and rotate it. The problem with that is we need to know how much to rotate. Well, what's the problem with that? Well, the way we express that is with a degree. Oh, we're going to rotate it 10 degrees, 20 degrees, 30 degrees. And for that, we need trigonometry, which that's a later course. Right? So we're not going to worry about that fourth kind of transformation. We're going to worry about just these three: translations, reflections, and dilations. So let's take a look at some examples of all of these transformations in action. First, we're going to take some examples of just individual transformations, and then we'll see some examples where several of them happen at the same time. All right, so example. Let's go ahead and graph f of x equals x squared plus 3, like this. So here, one way to graph something is to start plotting points. X is 0, x is 1, x is 2, x is 3, x is 4. Connect the dots. However, we know what this graph is supposed to look like, more or less. Notice that if you ignore all of the extra stuff here, meaning additions, subtractions, multiplications, divisions, if you just look at the most basic version of this kind of problem, it would look like this. Without that extra plus 3, this is basically just the quadratic parent function. Okay, so then I know it's going to have this kind of a shape. Well, yeah, but it won't look exactly like this because otherwise it would just be f of x equals x squared. Here I have f of x equals x squared plus 3. The extra plus 3 has to mean something. So the way we're going to do this is we're going to start off with our parent function. So here, let me do the parent function as over here in pencil. So here is the graph of f of x equals x squared. Okay. Here I'm going to label this as p of x, p for parent, just because I'm that kind of person who likes those kind of labels. So p of x is equal to x squared. Okay. Now, to get from here to here, I had to take my function and add 3 to it. Notice I'm not adding 3 to the x, I'm adding 3 to the whole function. Oh, that sounds familiar. If I add a number to the entire function, that's going to move everything up by that many units. So here, if I'm adding 3 to this function, it'll take this function, the parent function, and move it up 3 steps. So here, that's going to go up 1, 2, 3. And there we go. This point is now up here. Notice I don't need to graph a bunch of other points. It's going to have this shape. It's going to be this exact same graph facing in the same direction. It's going to have the same size. Everything about it will be the same. The only difference is it's now a little bit higher. Okay? And there you go. That's our function. You don't treat it as a bunch of different points. You treat it as an object. Oh, it needs to move up 3 steps. Okay, 1, 2, 3. There we go. All done. Let's take a look at another translation. Let's say now we want to graph f of x equals to x plus 2 squared. Notice this is still a transformation because I'm adding something, but now instead of adding it to the whole function, I'm adding it to just the x. Okay, so this is still, if you ignore all of the addition, subtraction, multiplication, division, in its most basic form, this is still just x squared. So I'm still starting with that same parent function. Okay, but now instead of moving it up, notice that my transformation is going to be a little bit different. Yes, I'm still starting with this original parent function, which again I'll label p of x equals to x squared. But now to go from here to this function that I want, I needed to add the number 2, but only to the argument, only to the x. Oh yeah, that's this right here. If I add a number to only the x, that's going to move everything to the left by that many units. Since I've added 2, it's going to move everything to the left 1, 2 steps. So this point is now over here, and we've got everything we need. We're just going to take that graph and just slide it over. It won't have a different shape. It won't have a different size. Notice it still looks exactly the same. The difference is it moved over to the left by 2 steps. And that's it. That's the graph of our function. That's our f of x. You can combine those. You can take a function and graph several translations. For example, let's go ahead and graph f of x equals x plus 1 squared minus 2. Notice that has several additions and subtractions, right? Well, yeah, but if I ignore all my addition and subtraction, this is still basically just x squared, which means it's still going to have basically just that shape. It's still going to be quadratic. But these extra sums and differences, this extra plus and minus, have to mean something. Okay, well, let's start off with just the parent function. Okay. Let me go ahead and graph this. Here's my parent function. I'll call that p of x equals to x squared. And now I have two transformations. Notice I have a plus 1, and that's inside my parentheses. Okay, well, that's plus inside the parentheses, plus to just the argument. That's going to move everything to the left. Okay, so that's going to be the first thing I worry about. This tells me I first need to move everything to the left by 1. Now you might say, well, wait a minute. How do you know that was the first thing you're supposed to do? Why didn't I do that one first? Does it matter? Order of operations. Parentheses go before anything else. So here, this plus 1 in the parentheses, that's going to be the first thing you handle. This is a subtraction outside of the parentheses. You worry about that later. Does it matter? If I switch the order, if I did this one first instead of that one, would it matter? It depends on the problem. In some cases, changing the order of operations, it'll still give you the same end result. In other cases, it won't. So, just to be sure, let's just follow the order of operations and make sure that we don't ever run into a case where it's going to cause a problem. Okay. So here we're going to do that one first. We're going to move everything to the left by 1. Okay, so let's go ahead and do that. Here, this point, we're going to move it to the left. And there we go. I'm going to redraw the graph. It's the same graph, same orientation, same size, same everything. It just slides over a little. Now, after I've done that, that minus 2, well, that's on the outside. I'm subtracting 2 from the whole function. Okay, well, that's going to subtract a number from the whole function. It's going to move everything down that many steps. So here, this is telling us to go down 2 steps. Okay, so that point will go down 1 and 2. From here down to here. So left 1, down 2. It's still going to have the same size, the same shape, the same everything. It's just in a different location now. And there we go. So go ahead and give this a try. Let's start you off with a different kind of function. Go ahead and graph f of x equals to, let's have you do absolute value of x minus 2, and then on the outside I have a plus 3. Okay? This won't have the same parent function. So go back to your list and see what's the parent function that this should have, and then apply the different transformations until you get your result. You do not need to do this by plotting individual points. You're going to do it this way. You're going to start with the parent function and transform. Go ahead and pause the video, give it a try, and once you have a result, go ahead and unpause and we'll do it together. So if you ignore everything but the most basic part of this function, if you ignore all the extra additions and subtractions, this is basically just the absolute value of x. And we know what that looks like. That's this graph. So this will be our parent function, which we will then modify. All right, so we're going to start off with our parent function. That's that V shape, like that. It's going to cross through the origin. And I'll call this P of x equals the absolute value of x. So now I have two things that I need to do. I need to worry about this minus 2, and I need to worry about this plus 3. The first one we do inside the parentheses. That's going to be that minus 2. So let's go ahead and do that. You're subtracting 2 from just the argument. Okay, subtracting from just the argument. That'll move everything to the right. All right, so from here we're going to go over 1 and 2. Still the same shape, same orientation, same everything, just moved over a bit. And then plus 3, that's to the entire function, not just to the argument. Okay, so plus 3 to the entire function. I'm going to move everything up. So here we're going to take this and we're going to go up 1, 2, 3. Still going to have the same size, same shape, same everything. It's just moved to a different spot. And there you go. That one in blue is our function. That's the graph of absolute value of x minus 2 plus 3. Let's take a look at some examples now of the other transformations. Let's graph f of x equals negative square root of x. All right, we know that if we ignore all the additions, the subtractions, the multiplications, all of that stuff, that's our parent function. All right, well, if we ignore that negative, this is basically just the absolute value of it. The square root of x. And we know what that looks like. That's going to have this parent function, the square root of x. So we're going to start with that as our parent function. It's going to start at the origin. It's going to go up and to the left and kind of curve a little bit, just like that. Okay. Now notice that we have only one transformation to worry about here. There's a negative. Whenever you have a negative, that's going to cause a reflection. And it depends on where that negative is, we're going to have a different kind of reflection. The negative is on the outside versus on the inside. If it's on the entire function versus on just the argument. Well, here it's on the whole thing. Right? It's outside the square root. Okay, so if you have a negative on the outside, that's going to flip everything upside down. It's going to reflect vertically. Okay, so that's what we have here. So that's going to cause everything to flip upside down. When we say upside down, we mean over the x-axis. So if something's already touching the x-axis, it's going to stay there. But that negative is going to flip everything that's up here. It's going to flip it down. So this is now upside down like this. And that's our graph. That's the graph of f of x. Let me go ahead and do on the same graph here just so we can compare. Let's go ahead and graph. Here I'm already using f on this graph, so let's use a different name. I'll call this one g of x. Let's graph g of x is equal to the square root of negative x. Just like that. Notice that's the same kind of transformation. I have a negative that's going to cause a reflection. But now, because that negative is on the argument, it's on just the x, like that, it's going to cause a reflection from left to right. It's going to cause us to reflect horizontally. So here's your parent function. If you're going to reflect horizontally, anything that's touching the y-axis is going to stay right where it was, but now everything that's on the right is going to come over to the left. If there was anything on the left, it would have gone over to the right. Everything flips over across the y-axis, just like that. So note, your negatives cause a different kind of reflection. If it's on the entire function, this comes down, upside down. If it's on the argument, on the inside, this comes across, reflects horizontally, left to right. Let's take a look now at a dilation. Let's go ahead and graph f of x equals double the absolute value of x. Once again, if you ignore all the additions, subtractions, multiplications, and divisions, that gives you your parent function. Here, if you ignore that multiplication by 2, this is basically just the absolute value of x. And again, we've seen that one a couple of times. That's going to have this parent function. All right, so let's start with that. Here's our parent function, the absolute value of x. And now let's look at the transformation. Here you're multiplying. Because you're multiplying by a number, in this case the number 2, that's what's telling you that you're going to have a dilation. And it depends on where that multiplication occurs, that'll tell you what kind of dilation you have. Here, you're multiplying on the outside. You're not multiplying the argument, you're multiplying the entire absolute value of x by the number 2. Whenever you multiply on the outside, that's going to make things either taller or shorter. And again, it depends on what that number is. If that number is bigger than 1, everything will get taller. If it's less than 1, everything's going to get shorter. Okay, so here that's the number 2, that's greater than 1. So we're multiplying by a number that's greater than 1 to the whole function. All right, here we're multiplying to the whole function. We're using a number that's greater than 1, so the whole thing will get taller. When we say taller, we mean everything will stretch upwards. Notice we don't want this to get any wider or skinnier. We're just going to make it taller. Here, this number 2 makes everything twice as tall. So here, however much it went up before, it's going to go up twice as much now. Notice it's not going out any further. It's only going up higher. Same thing over here. This is now up here. Anything that was on the x-axis isn't changing. Why? Well, think about what happens if you were to plug in that number. If you were to plug in 0, what's double 0? It's still 0, so that hasn't gone anywhere. So anything that was on the x-axis hasn't changed. So it's going to make everything taller. In this case, twice as tall. And there we go. Just like above, I'm going to go ahead and put the other one on the same graph just so that we can compare them all. Let's go ahead and graph g of x is equal to the absolute value of, let's use the exact same number. Absolute value of 2x. Like that. Okay, so now here you're multiplying on the inside by that number. Okay, so let's see, that's going to be this one here. You're multiplying by a number on the inside on just the argument. Here, the number is the number 2, so that's this one here. And it's going to make everything more narrow. So it's going to be twice as skinny. If that may sound a little strange here. If I do that, it's going to make it hard to see because they're going to be so close together. Let me use a different number here. Let me use 1/2 instead of 2. There we go. So now, again, I'm multiplying on the inside. Now I'm multiplying by a number that's less than 1. Okay, so that's multiplying on the inside by a number that's less than 1. We're going to make everything wider. Okay, so that's going to make everything wider. It's still going to go up. It's still going to come up the same amount, but now it's going to be wider out like this. If it's 1/2, it's going to be twice as wide. If it's 1/3, it'll be 3 times as wide, and so forth, like that. And that's our result. And of course, we can always combine those. So give this a try. You're going to start with the parent function, and then you're going to modify it using whatever transformations are appropriate. So go ahead and try this. Graph f of x is equal to negative 2x squared. Notice here you have one operation, but really you have two. There's two transformations here. You're multiplying by a number and you have a negative. When you multiply by a number, that's going to cause a dilation, but a negative is going to cause a reflection. So give that a try. Pause the video and note that you do have two separate operations. Once you have a result, go ahead and unpause the video and we'll go through it together. So we're starting with the parent function here. Note that if you ignore everything besides the most basic operation, if you ignore all additions, subtractions, multiplications, and divisions, it's basically just x squared. So our parent function is the parabola. Okay. parabolas are supposed to be uniform. The left side should look the same as the right, so let me not make it lopsided. So there we go. So there is our parent function, p of x equals x squared. So now I have two operations to handle here. Now here they're both the same kind of operation. In the previous example, we saw, okay, I have two operations, and which one do I handle first? Oh, there's one in parentheses and the other one is not in parentheses. So one in parentheses goes first. Here, they're both the same kind of operation. You're multiplying, right? Multiplying x squared by a negative and the number 2. Okay, so here, there is no reason why you need to do one over the other. So if you did the reflection, then the dilation, or if you did the dilation, then the reflection, you are going to get the exact same answer. So here, I'm going to do the dilation first and then the reflection. If you did it the other way around, that is also correct. So I'm going to go ahead and do this in 2 stages. First, I'm going to do the dilation. Okay, I am multiplying x squared by the number 2. Or in other words, I'm multiplying a parent function by a number that's bigger than 1. Okay, so here's a parent function, and I'm multiplying it by a number that's bigger than 1. Okay, so it's going to make everything taller. So here, this is still going to have the same shape, it's going to point the same direction, but now everything's going to be twice as tall. Looks like that. Okay. Now, this negative, note again, that's on the outside. If it was on the inside, that would be different. On the outside, it's a vertical reflection. You're flipping things upside down. So that negative on the outside is going to make everything upside down. So we're going to take the dilated parabola, the one that's already taller, and they're going to flip that upside down. All right, so now that's this had a height of 1. Now it's got a height of 2, but now it's going to come down 2. It's going to be upside down. It's the same shape, same size, but now it's upside down. And there's our function. There's our graph. Finally, as our last example for the section, we can combine all of these kinds of transformations. There's no reason why you have to just combine these 2 or just these 3 or anything of that nature. You can combine any and all types of transformations. So, as our last example, let's go ahead and graph the function f of x equals, let's say 2 times x minus 3 cubed plus 1. Okay. You can tell I work very hard to come up with examples 1, 2, and 3. Okay. All right. So first of all, start with your parent function. Note that this, if you ignore all additions, subtractions, multiplications, and divisions, I'm going to need another pencil, aren't I? This is basically just x to the 3rd power. And we know what the parent function of x to the 3rd power looks like. It's this one here. So we're going to start off with that as our parent function, and then we're going to modify it as we need. Okay, parent function is x to the 3rd. Okay, now here, when you have several types of transformations, it really is important to be able to put them in order. The more operations you have, the more it'll make a difference if you do them in the wrong order. So here we're going to follow the order of operations. Fortunately, we've already known the order for many, many years, right? Parentheses, exponents, multiplication, division, addition, subtraction. Okay, I have some parentheses right here, so the stuff inside goes first. Then I have some multiplication, and then I have some addition. Multiplication goes before addition. Parentheses, multiplication, addition. So I have 3 different transformations. I'll call this one right here. That one's going to be the first one. I'll just call that one number 1. This is going to be the second transformation that I do. I'll call that one number 2. And that's the third transformation that I'm going to do, and I'm going to call that one number 3. Okay. All right, so my first transformation has me take my function and simply, well, minus 3 on the inside, minus 3 to the variable, minus a number from the variable. That's going to move everything to the right. And since that's the number 3, it's going to move everything to the right 3 steps. So it's going to be 1, 2, and 3. I'm going to redraw the same graph, same size, same shape, same orientation and direction. Let me erase that so it's not in my way. And that's going to be, here I'm going to label this as P for parent. I'll label this as number 1. That was my first transformation. Now, the number 2. I am now multiplying the entire function by the number 2. Okay, I'm multiplying on the outside of the function by a number bigger than 1. Okay, I'm multiplying on the outside by a number bigger than 1. It's going to make everything taller. And in fact, it's going to make everything twice as tall. Yeah? So now, I'm going to take this graph. Let me make these shorter at the beginning, just so that when I make it taller, it doesn't go so far off my page. Okay, so here's my my parent function. There really should be a little more curved. There we go. That's my step number 1. Step number 2 is going to make everything twice as tall. I'm still going to go out this far, but I'm going to go up twice as much. So it's going to be like this. And then again, over here, I'm still going to go out this far, but I'm going to go down twice as low. And finally, that plus 1, that's going to be my third step. And that's just going to move everything up 1 step. So right here, this was right here. I can move everything up 1 step. And it's still going to have the same size. So it's going to be twice as, it's still going to be this tall one. It's going to have the same size, the same shape, the same direction, same orientation. It's just going to be lifted up a bit. So this is our function. We took our parent function. Step number 1 had us move it over to the right 3 steps. Step number 2 had us made that taller, twice as tall. And that plus 1 had us take that tall one and move it up 1 step. And now here, this one in blue is our graph. That's our function, the one we want. You don't treat these all at once. You treat them one at a time, and you modify your parent function 1 stage at a time until you get your result. Notice that at no point did we plug in any numbers. We never said, okay, if x is equal to 0, what happens to y? If x is equal to 1, if x is equal to 2, don't worry about that. We start with the parent function and modify, which it can take a few moments to do that, but it is almost always going to be significantly faster. There is one trade-off to this. Notice we are missing some details. We don't really know what this point is. All right? We don't know exactly what these points are up here. In the next chapter, we're going to see how to take these parent functions and how to lend them some more details. This isn't going to go away. This is still going to be the basis of what we're doing. But once you have these basic shapes, once we have these basic graphs, then we can start adding details to these basic graphs. It's sort of like, here's this, if anyone does any drawing, if anyone's taken any art classes, things like that, if anyone just likes to draw for their own sake, this is the sketch. We haven't done any shading. We haven't done any of that stuff. We haven't added any of the details. Here we've only done the sketch. All right. So go ahead and let's go ahead and finish off the section. Go ahead and give this a try. Go ahead and graph. Oh, let's see. Let's have you try f of x equals 1 over 2, 1/2, times the square root of negative x, let's say minus 4. Notice this minus 4 is on the outside here of the square root. So go ahead and give that a try. Remember, you have a few different operations, which are going to cause a few different transformations. As you handle those, make sure you're doing them in the order of operations: parentheses, exponents, multiplication, division, addition, subtraction. Go ahead and pause the video and give this a try. Once you have created a graph for this, go ahead and unpause the video, and we'll go through it. We'll go through it together. All right. So here, if you ignore everything but the most basic function, if you ignore all the additions, subtractions, and multiplications, this is basically just the square root of x. So we're starting off with the parent function square root of x. And that's this graph here. Okay. Now we have three transformations. Note that you have in your square root, which does act like parentheses. This does act to keep everything in here together. You have one operation here, so parentheses go first. So this minus will be our first transformation. All right, well, let's see what that is. I have a minus on the inside of a function. I have a minus on just my argument. Oh, I have a minus on just my argument. That's going to be a reflection left to right. So let me take this graph and reflect it left to right. It's going to start from here and going to go up in this direction. Notice it's got the same size, the same shape. Everything about it's the same, except that now it's pointed in the opposite direction. It's reflected left to right. Like that. Okay. So now our next transformation, well, let's see, I'm multiplying by a half and subtracting 4. Well, yeah, multiplication needs to come before subtraction. So let's go ahead and do that. Multiplication, that's going to be our step number 2. Here's my parent function. Here's step number 1. Step number 2 has me multiply by a half. Okay, so I'm multiplying on the outside of my function. I'm multiplying the entire function by a number that's less than 1. Okay, so I'm multiplying the entire function by a number that's less than 1. It's going to make everything shorter. So, because that's a 1/2, it's going to make everything shorter. It's going to make it half as tall. So here, instead of coming up this far, it's only going to go up half as far. So this is now a shorter graph. Notice it still comes out the same amount, just doesn't go up as much. It's half as tall. And finally, the -4. Well, now I'm subtracting something from the entire function. It's not on the inside here. It's subtracting from everything. Okay, well, I'm subtracting something from the entire function. It's going to move everything down. And in this case, since that's a -4, it's going to move everything down 4 steps. So this short graph that's flipped over to the left, it's going to go down 1, 2, 3, 4 steps. 1, 2, 3, 4 steps. Notice it's still the same size, the same shape, the same direction. Everything's just moved down a bit. And there we go. Again, note that we don't have any details on this. We don't know what any of these points are. In fact, the only one we kind of do know is this. Well, in fact, the only one we do know is this one here. Notice this was at 0, 0, and it went down 4 steps. So this one's now at 0, 4. Oh, that should be -4, right? 0, -4. So because of the transformations, whatever started at the origin, you will still know where that is. Because, okay, I moved that 2 steps to the right and down 3 steps. Oh, so then it's at 2, -3. But aside from whatever this point was, we don't really know many other details. There's nothing wrong with that for now, but in the coming sections, we'll see how, in the coming sections and in the coming chapters, we'll see how to add the details on top of these basic structures. But for now, that is it for this section. If anybody has any questions, comments, problems, please make a note of those and reach out to me. You know how to reach me, either next time we meet or at through an email. Okay? I hope everyone has a nice day.